basically turning it into an unconstrained maximization problem. The second way is that Lagrangian multiplier. Lagrangian multiplier. So this will be, you prove this in some more advanced calculus courses, but we just need to know how to apply it here. And so essentially, we kind of reformulate the problem as we're trying to as this Lagrangian equation is, usually it's like, it's capital L letter, you can just write normal L if you want, equals this utility function minus lambda, this is the symbol lambda, and then we have our budget constraint in here. So this is some kind of like new variable. And this is what we refer to as the Lagrangian multiplier. And so what it is our optimal choice has to satisfy three equations. And they have to do with taking the derivatives of these Lagrangians, of this Lagrangian equation here. So it's the derivative of L with respect to x1, the derivative of this L with respect to x2, and then the derivative of this L with respect to lambda. And we're going to set them all equal to 0, and then we're going to have three equations and three unknowns, and we'll be able to solve those. So this is just the derivative of u. When I say u in brackets with a dot, I just my shorthand instead of writing x1, x2. So the derivative of this utility function with respect to x1, and then the derivative of this with respect to x1 is just minus times lambda p1. So that equals 0. At the optimum, this is also satisfied. We're doing the same thing for 2. And if we take the derivative with respect to lambda, we just get this budget constraint, right? We just get p1 x1 star plus p2 x2 star equals m. I'm putting stars there, and if I wrote these utility functions out completely, I'd put a star there, because these are the three equations that are satisfied when we have this optimal choice. So here we have three equations and three unknowns. So the unknowns are lambda, x1 star, and x2 star. And so we're just going to solve for those. We're first going to kind of solve for lambda, and we're going to solve for the rest of them. Take the ratio of equations 1 and 3, sorry, equations 1 and 2 in terms of those partial derivatives. And so then we get exactly what our x1 star, x2 star, we get exactly the condition we had before. So if we did that, if we put that first equation from that last board over the second, we divided them, we get exactly this. And we still have that third equation, which is just the budget constraint. Now we have two equations, two unknowns. And so we can solve for x1 star, x2 star as a function of m and then the prices. So income and the prices. You know, when we actually, I'll show you a calculus in a couple minutes here. You know, we'll actually solve for lambda and solve for it, but essentially we can break down this Lagrangian into the problem we began with when we have two equations and two unknowns and we just solve for it. So you just take the ratio of those first two partial derivatives of L with respect to x1 and L with respect to x2, take the ratio of those and we get this. And then that third partial derivative with respect to lambda is just a budget constraint. We're kind of back to what we've seen before in terms of two equations and two unknowns. But let's go through an example of the Cobb-Douglas preferences in terms of these different methods.